Hey, welcome back to Algebra, Describing Systems and Predicting. How you going? It's getting interesting, isn't it? Trying to find a description of all these things that we've been doing, the paper folding and the regions of the circle. And have a look at this screen. This is a pretty busy screen here. And I've got a question for you. As usual, start off with a little question in here. What do I do to this to get that? What does that mean? Well, we've been generating some data sets, and we've got tables of values like this with paper folding, and we were trying to work out how to do this, weren't we? Could you see a pattern? Could we use maths or algebra to describe it? And can we then predict? And in the last presentation, I guess you all got a shock because, what? We found that you can't always take a few examples and then go on and say it's always going to be that way. You've got to be able to prove it. And we had to look at paper folding, we could prove that. But the regions didn't work after n equals 5. Do you remember that? Anyway, so that's what we're trying to do. So when you look at a table like this, or like this, getting harder, how do you build up skills to work out what do you do to this to get that? That also will work for this to get that, and this to get that. So we've got some examples around the screen, and this is going to be an exciting presentation because what I'm going to do is to get you to have a go and then see if I can teach you some little tricky do's to be able to work out what do I do to this to get that. Okay, come on down now and let's have a look at the first question. Hey, I reckon you should be able to do this. What do I do to get to one to get one? Nothing? No, you're not allowed to do nothing. Let's write some things down. What do I do to one to get one? Multiply it by itself. Could do that. Or I could double it and then divide by 2. That'd be 1. What else could I do? Multiply 1 by 3. 3 times 1 is 3. And then take 2 would be 1. So you can see there's whole heaps of possibilities when you've only got, well, particularly 1 going to 1. But it's when you get other values that have to produce a certain pattern. And what's the pattern? That's what we're trying to say here in algebra land. So let's come down and build this a bit. What do I do to 1 to get 1 that will satisfy the question, what do I do to 2 to get 3? Well, what do I do to 1 to get 1? Oh, too many there. What do I do to 2 to get 3? What's an example? We could multiply it by 3. 3 2's are 6. And take 3, that'll give 3. Would that work back here? 3 times 1 is 3. Take 3. No, that gives 0. What's something else? We could multiply 2 by 2. That's 4. And take 1. That'll give 3. Would that work here? 2, what are we doing? 2 times the n value, take 1. Check it back here. 2 times 1, take 1 equals 1. Works. You get the idea. To a certain extent now, at the moment, it's trial and error. And you've got to check back because what do I do to this to get that has to work for this to get that. All right, let's keep going. Let's build it up a bit. Here we are. Here are some possibilities. I've just done this one here. Here's another one. Did you think of that? A half of 1. Oh no, here, we'll do it a bit more easily. This would be 1 plus 1 is 2. So it'd be a half of 1 times 2 is going to be 1 again. So in other words, add 1 onto this and get 2. Halve it, get 1. Okay, and you multiply by itself is 1. Let's do it for this one. Does it work for this one? What is n? N is 2, and then 2 plus 1 is 3, which is 6, and then halve it. Yeah, it does work. In other words, multiply the number by 1 more than the number, and then halve the whole thing. That's what this is saying. Well, that's complicated, that one. That's complicated. What's this? What's going on here? This is powers. Let's have a look at whether this one works now. This says get 2, raise it to the n. So let's go to n is 1, this one. That'd be 2 to the 1 minus 1. Yep, that works, that gives 1. Let's check it for this one. This would be 2 raised to the n is 2 to the 2, take 1. That's 4 take 1 is 3. That works. So we've got some rules. Now, let's build it a bit, because this is only a little table, isn't it? What happens when we come to this one? You can see the problems. Now we've got 3. What do I do to this to get that? It's got to work for all of them, doesn't it? We want to spot the pattern and get a formula, or use algebra to describe it, and then predict. That's what the journey is here now. Okay, well, multiply by 2, take 1, worked for these two. Does it work for this one? No. 2 times 3 is 6, take 1 is 5. So that one's out now. See the process that we can use? Let's put n is 3 in here. This is a half of 3 times 3 plus 1 is 4, half of 12 is 6. No, that doesn't work. It's supposed to be 7. Is this one still in the ball game? Let's do it. 2 to the 3, take 1. That's 8, take 1 is 7. Oh, it works. So there's a rule that is still surviving. Do you get the idea? As we go along, a bigger set of data here that we got from paper folding or the regions, so it gets more and more difficult to get a unique pattern that says, no, it doesn't have to be unique, a pattern that still holds for each one. What do I do to this to get that? Okay, what about this one? This is an interesting one. Does it work for n is 1? 1 squared, take 1 plus 1. Take 1 plus 1 would just give 1. Yep. How would you think of this though? I wonder. Put in n is 2. 2 squared, take 2 plus 1. 4 take 2 plus 1 equals 3. Oh, it does work for that. Let's check the last one. N is 3. It'll be 3 squared, take 3 plus 1, which would be 9 take 3 plus 1, which would be 6 plus 1 is 7. Hey, that complicated pattern works. The question is, how would you spot that one? That might be a bit hard. Okay, so do you get the range of things we're trying to do to see a pattern and describe it and then predict? Come down and let's have a look. What have we been doing? Here we are. You should have realised that what we've been doing here is developing a way of determining the possible algebraic expression or surname, if you go back to the old family's introduction to algebra, that will describe all the members. Okay, and the thing is there also, we have to check it out for all the examples we use. And even then, we can't be sure that it will keep going. Remember the regions exercise from the last presentation. Even though we have a pattern, we really want to have a proof or some reason for saying it's always going to keep going so that we can predict. Okay, let's go down and it's your turn. Okay, something for you to practice. All right, write down 5 different ways that 3 can be operated on to get 11. Okay, so I want you, that's the next one, so just come to here. 5 different ways that 3 can be operated on to get 11. I want you to pause the presentation and see if you can find the 5 different ways. Okay, 5 different ways. Right, pause it, have a go, talk to your classmates and check each other's out. I'll give you a few possibilities. Okay, what are a few possibilities? 2 times 3 is 6 plus 5 is 11. Oh, we could just have the first one. 3 plus 8 is 11. Or you could have, 3 squared, 3 by 3 is 9, plus 2 is 11. What could you have? Maybe 2 cubed, use the 3 as a power, 8 plus 3 is 11. Yeah, complicated, isn't it? Lots of things you could do. You can multiply 3 by 1 more than 3. That's 3 by 4 is 12. And then take 1 to get 11. Okay. So in n land, what would this be? This would be n by n plus 1, take 1, where you're playing with 3 in there. This would be 2 to the n plus 3 is 11. Do you get it? And here it would be n squared, because n is the 3 we're playing with. N squared plus 2 equals 11. You're starting to get the hang of algebra? That's describing a whole family? I hope so. And n is the generation number. N is the changing value which will enable you to generate members of the family through an algebraic expression. All right, let's build that a bit. So here we are. Write down 5 different ways that 3 can be operated on to get 157. Okay, I want you to pause the presentation, maybe discuss it with your classmates and see if you can come up with a few. Right, I'll give you a few. So let's start with n, which is 3, and just add 154. That gives you 157. What about timesing it by 2? 2 times 3 is 6 plus 151. That's 157. There's an infinite number of possibilities. This is n plus 154. This is 2n plus 151. Okay, what about something different? What about 3, which is n? We'll go 3 to a fairly high power. What? 3 to the 4 is 81. We could go 3 to the 4. That's 81. And we'd have to add 76, wouldn't we? Yep, add 76 is 157. And this would be n to the 4th plus 76. That idea is 157. What about 3 by 3 plus 1 by 3 plus 2? What's this? This is 4, 5. And can we do another one? 3 plus 3 is 6. What's that, 1260? No, that's too big. I won't do that. I don't want to go past it. So let's go to here. 3 by 4 is 12. This is 60. And then if we times by another 2, 120. Okay, that would give us 120, and that add 37. Oh, and this could go on forever, couldn't it? Okay, so that's what we want you to think about. Ways, what? Ways of thinking. For short, what? Okay, ways of thinking. So think about these patterns in different ways. Powers and timesing by the number itself, powers of itself or powers of 2. Okay, let's try and build on that now. Okay. Here's our problem. What do I do to 1 to get 2? But then you've got to move on. What do I do to 1 to get 2, but 2's got to go to 6? And then 1 to get 2, 2 to get 6, and 3 to get 12. There's several conditions, aren't there, when you're in a table like this, right? It's got to do that, and that, and that. This is where the headache comes in. Okay, so what I want you to do is to pause the presentation and see if you can do this one. Okay, what do I do to this n value, this is generation number, to get the set of members of the family? Okay, so pause it and have a go. All right, so we could try a few here. What could we try? Well, in this first one, if you double 1, that's 2, but it doesn't work here, and it doesn't work here. So what could we try? Maybe squaring them? Could we square them? 1 squared plus 1 is 2. Is 2 squared plus 1 6? No, it's 5. So that doesn't work. What about multiplying 1 by 1 more than 1. 1 plus 1 is 2. What about doing it for 2? 2 times 1 more than 2. Oh, that works. And what about 3 times 1 more than 3 is 12. Oh, I think we've got it. So get the number, generation number, multiply it by 1 more, and that will give us our m value. You see what we're doing? What do I do to this to get that? Okay, and then you've got to check them out. It gets harder the bigger the table is, doesn't it? It gets harder. And what we want to try and do is, you could have seen it this way. We've got a doubling here. Oh, we've got a doubling here. We've got a tripling here. So this way is harder to see in this particular case. And what we want to do is predict. Remember, the last step in all of this is to predict. So we want a rule saying, what do I do to this to get that? So that we can pop right out here and say if n is 100, we can work that out without going along one answer at a time. Recursion, that's called. Then again, we've still got to question our prediction, don't we? Because we've already found that a pattern can hold for a while, but not forever. So we've got to actually prove that pattern. All right. Let's go to another one. So give you a bit of practice here. Well, here's the next one. And then we're going to use it to predict. All right. So I want you to pause the presentation and see if you can work out what do you do to that n to get this m and so on that works for all of them. Okay. So pause it and have a go. All right. Let's come back and we can try various things. Multiply this by 2 gets 2, but it doesn't work here. Multiply this by 2 gets 6, but it doesn't work there. Okay, so it's going up by 3 and then 5. So we could do this forever to get out to a particular point, but what we're looking at is this way. This is called recursion, where you recur, the pattern recurs along here, and you use one answer to get to the next one. But we want to go out here and say I can predict that without all these in between. All right, so multiply 1 by 2. That's no good, it gives 2, but it doesn't work there. What about n by m plus 1 again is 1 by 2, but 2 by 3 would be 6. That doesn't work, the n by n plus 1. Anything else you might try? What about powers? 2 raised to the 1 is 2. 2 raised to the 2 is 4. Okay, 2 raised to the 3 is 8. Well, 2 1 to the 1 is 2 is works. This one doesn't, and this one doesn't. So what can you do there? Is there another way of doing it? Okay, so here maybe can you work with powers of these? So 1 squared is 1 plus 1. Maybe square the number and add 1. 2 squared is 4 plus 1 is 5. 3 squared is 9 plus 1 is 10. I think we've hit it here. In other words, take the n, square it, and add 1. Okay, what about that? That seems to work. Okay, so what we've tried to do is try sort of multiplying the number and adding things, then powers of the actual n value, and then, no, this is powers of 2 to the n. This is 2 raised to differing powers there, and then use the n and powers of it and try those things. So we've got a few things to work through and check them out as we go along these 3 entries. So if n was 15, m should be n squared plus 1, which is what we've said. So if n is 15, 15 squared plus 1, might have to do this on the calculator, is 225 plus 1 is 226. That's if the pattern kept going. It doesn't always, does it? We are what's called extrapolating, doing extra points out along the pattern. We mentioned this in an earlier presentation, extrapolating. We really should prove somehow that the rule would keep working there. But what we say here is if this rule still applies, if nothing changes, then the answer would be 226, and we've predicted. Just keep in mind, there is a reservation here. When you extrapolate, go further points, you really need proof that it will keep going. All right, come down and let's have a look at this one. I think this is your last one here. We'll have a look in a minute. No, there's something coming up down the bottom, I see it. That's predicting, I think. I think this is the last one. Yep. Okay, so if n was 11, what do you think m might be? Okay, so we need to look at the pattern. What do I do to this to get that? Okay, and so what could I say here? Oh, what do I do to 1 to get 3? 2 times 1 plus 1 is 1. And then 2 times 2 plus 1 is 5, yes. And 2 times 3 plus 1, that was an easy one, is 7. Okay, so that's an easy one. Let's say here, therefore, m is 2 times n plus 1. Okay, this is quite difficult, isn't it, to get your head around what you try. So we're trying at what's called a linear model here, where you just multiply the number, the generation number n, by some whole number and add or subtract. Well, it doesn't have to be a whole number, it could be a fraction, and you play with that. So that's not a bad one there. Okay, so if n was 11, what do you think m might be? M would be 2 times 11 plus 1, which is 23. With the proviso that it keeps going. Just remember, we should say we are doing extra points, extrapolating, and it may not work. But if the pattern held, the pattern that we've proposed up here, hang on, let's just stop that now. We've just got to lose that a little bit. Sorry about that little hiccup. So we're talking about this extrapolating. So there you are. Think about that. I think, is there one more for you? I don't think so. Oh, yes, there is. Oh, there's one. Okay, so come down and let's have a look at this one. Getting a bit harder because you've got 4 of them that you've got to worry about. Okay, so what would you do here? Well, you could try multiplying. We won't start with this one. So many things work with 1, as we found before. We could say 4 times 2 plus 1. And then that works. 4 times 3 plus 1 doesn't work. Too small. It's got to give 28. So I think we need to get something larger. Look how they're growing. They're growing very rapidly. Maybe powers. Okay, maybe powers of something. Okay, so what could we do? What could you do to 2 to get 9? Well, let's cube it. 2 to the 3 is 2 by 2 by 2. 8 plus 1 is 9. That makes it grow very rapidly, this power, doesn't it? There's an interesting point. So can we do it with 3? 3 cubed plus 1. Would that work? That's 3 by 3 by 3. 27 plus 1 is... Oh, it's working. We better go back and check out 1 though. 1 cubed plus 1. Yes, that's working. So just this last one to check. So 4 cubed plus 1 is 4 by 4 by 4 plus 1 is 65. So our rule is, little m this time, equals n cubed plus 1. Great. Okay. We're not going to predict here. but we could put in bigger values of n out here, and if the rule held, then we could predict. Okay, so get the idea in this one. There was a big gap here. The number had to increase rapidly. So that suggests powers of either itself or another number. And this time we've raised the number itself to a power to make it grow more rapidly. Are you getting the hang of it? It's an interesting puzzle, isn't it? All right, that's all we're going to do for the moment. So cheers for now.